Welcome to the Math 1 lesson summary video for the task Connecting the Dots, Piggies, and Pools. The purpose of this task is to extend knowledge of arithmetic sequences onto linear functions and to extend knowledge of geometric sequences onto exponential functions. So sequences are just a list of numbers. Functions are comparing a set of inputs with a set of outputs. So we have a more detailed context that we're going to be looking at in each of the four scenarios of this task. So in scenario one, we have a person whose little sister, Savannah, has a piggy bank that she wants to fill. And so the essential information that comes out as you read over this is that she's starting with 5 pennies, and each day when Savannah's sibling comes home from school, she gives her 3 pennies. So from that, we can write a recursive rule, and notice that they're asking us to model the number of pennies of the piggy bank on day n. So as we're used to, we're going to use n. I'm going to use p of n though, and p in this case is representing the pennies, just to emphasize that we're really comparing two things. We're comparing the number of days with the number of pennies. So in this case, we're going to have a recursive rule, p of n equals p of n minus 1 plus 3, because she's adding 3 pennies every day, starting from a point p of 0, which was 5 pennies, where she began. And so I wanted to find a couple of vocabulary terms off to the right side of the screen here, and the first one I want to talk about is the domain. The domain is the set of all input values for a function. So in this case, as we think of n, the number of days, we have to think about what kind of values could I input to this function in this scenario. And so this is really called the practical domain, the domain that makes sense in this scenario. So could I input a negative number of days in this scenario? No. So we already know that our domain has to be positive numbers. And then because of the way this is set up, where she's giving her pennies each day at a set point, it doesn't really make sense to put in non-integer values either, non-whole number values. So we're only going to be inputting whole numbers. So our domain for this function is just the whole numbers 0, 1, 2, 3, and so on. So now that we've gotten that, we can make a table and a graph. So I've already taken the liberty of getting it set up for us in Desmos. You can see it's starting at 5 pennies and then adding 3 each day, going up to 20 by day 5. And again, to add a table in Desmos, you just click on the add item and put a table. And so now we want to write an explicit rule. So again, I'm going to use p of n, and we're starting, using what we learned in the last unit, we're starting from 5 pennies, we're adding 3 each day, so that's going to be 5 plus 3n. And we get this line right here, this graph. And so now we want to talk about the two other vocabulary terms, which is discrete function versus continuous function. So the set of points that I've plotted represent a discrete function. They're not connected because as you can see, there's gaps between the dots, whereas this right here represents a continuous function. And so the question is, which makes more sense in this scenario? And the discrete function really makes more sense in this scenario. This rule is still correct, this explicit rule is still correct, but we would only look at the input values of whole numbers. So if I were to take a look at this, I wouldn't want to look at points like this that are decimals. I would only want to consider the points like 6, 23, because it's a whole number input, which consequently yields a whole number output. So this is a discrete function. And a discrete function is a set of distinct values, whereas a continuous function is a set in which the elements can take on any value within the given interval. So to look at a continuous function, let's go on to problem 2. See in problem 2, the key pieces of information are that there's 5 gallons of water in the pool when she decides that she doesn't want to stand and watch it, and then she notices that it's being filled at 2 gallons every minute. So we can write a recursive rule, w of t equals w of t minus 1, is plus 2 for the 2 gallons every minute, and w of 0 is 5 gallons that we started with. So in this case, W is representing the number of gallons in the pool, and T is representing the number of minutes. So using that recursive rule, we can generate this table. And so we have starting at 5, adding 2, we get this table. So at 5 minutes, there'll be 15 gallons in the pool. And now we can write an explicit rule, W of t, t representing the minutes, equals 5 plus 2t. So in this case, again, only the positive quadrant makes sense for our domain because we can't have negative minutes of filling the pool in this scenario. And the question is, do we want the disconnected or the continuous? So the discrete or the continuous graph. And in this case, we want the continuous graph because in between each point, all these values make sense in the context. So at 3.42 minutes, there was 11.84 gallons. At 3.54 minutes, there was 12.08 gallons. At 3.6 minutes, there was 12.2 gallons. All those values make sense in the context. Whereas in scenario 1, the values in between the data points don't make sense in the context because the giving of the pennies only happens at a set time each day. So those are some differences, this one being discrete, this one being continuous, but they're similar because they're both arithmetic sequences starting at 5. This one is growing faster than this one because the common difference here is 2, whereas here it's larger, it's 3. So those are some of the similarities and differences when you get to the later problems and it asks for those. So let's go down to problem 3. It says, this girl is more sophisticated than her sister, so she saves money in a bank account that pays her 3% interest on her money. So the key piece of information is that she's making 3% interest at the end of each month. So there's set times again off of the $50 that she got for her birthday. So what you might start off doing is you'd say, okay, so I need to do 50 times 0.03 to find 3% of 50, and I need to add that with 50. And what we can see that that's actually equivalent to is if I use I'll call it the reverse of the distributive property for now because we haven't learned about factoring, that would be the same as 50 times 0.03 plus 1. So you can see if I distribute this, I'll get the same thing that's above. So I can simplify this process by just multiplying by 1.03 instead of multiplying by 0.03 and then adding 50. So that helps me to write my recursive rule. So A of M, where A stands for the amount of money and M stands for the months, equals A of M minus 1 times 1.03, starting from an A sub 0 of 50. So now we can make a table for this scenario as I've done already here in problem 3. So we're starting at $50, then going up to $51.50, and so on, multiplying by 1.03 every time. And I need to zoom out in order to be able to see this. Again, only the positive quadrant makes sense for our domain because we can't have negative inputs in this scenario, in this context. Or they wouldn't make sense in this context. So again, the question is, do we want to connect these points or not? And because the account interest occurs at set times each month, we wouldn't want to connect these points, and this is a discontinuous function. And we can write a explicit rule for this function. So geometric sequence this time, so we're using what we learned in our last unit. For geometric sequences, we always start with the starting amount multiplied by the common ratio raised to the power of m in this case for the number of months. And so even though that function appears continuous, we would only want to use the data points along there that are whole number inputs. The outputs in this case, it's okay for them to be decimals because it's representing money. So we would continue on just using the data points in a discrete fashion. And that's problem 3. So now let's compare problem 1 to problem 3. They're both discrete, but this one was an arithmetic sequence with a constant difference. And so that's a linear function. You can see it's a straight line when I create the explicit rule. This is discrete, but it's a geometric sequence, and so it's got a common ratio, and it's a curved function, which you can see the curve much better if I zoom out a little bit. So notice a geometric sequence create curved exponential functions. So that's interesting. And so then we can finish off with problem 4. So in problem 4, similar idea. I have the pool scenario again. It's the end of summer now. She's draining a gallon swimming pool at 3%. So this time I would multiply the 15,000 times 1500 times 0.03, and I would subtract that from 1500, and I'd keep repeating this process. So a simpler way of doing that is if I use the reverse of distributive property, that's 1 minus 0.03, which is going to be 0.97. So you can also think of it as if it's losing 3% of the water in the pool, it's keeping 97% of the water in the pool. So we can write G of n, G of t, where G is representing the gallons, T is representing the minutes, equals G of t minus 1 times 0.97. That's a recursive rule. And in this case, G of 0 equals 1500, the original amount of gallons in the pool. So we can make another table from that recursive rule. I've already done that for us. So you can see for this one, I'm going to need to change the settings. So let's go 0 to 100 minutes maybe as an estimate for how long it will take for the pool to unfill. We already know 0 to 1500 gallons is going to make sense. So we can see that gives us a nice picture. So the explicit rule is going to be G of t equals 1500 times the common ratio 0.97 raised to the t power, just like we learned back in module 1. So you can see I was pretty close with when it's going to get down to empty. It's getting closer and closer there, around 100. But in this case, this is a continuous function again because the pool is constantly draining. There's no set amounts where it like just 2 gallons magically disappear and then another 2 magically disappear. It's continuously flowing out. So all of these points on this graph all make sense in context. So this is a continuous function. So comparing problem 3 and problem 4, problem 3 was discrete, problem 4 was continuous, but they're both exponential functions because they come from geometric sequences. That's about everything that you need for this task. I hope you enjoyed watching. If you need help with the Ready, Set, Go problem specifically, please check out the Ready, Set, Go videos in the Canvas support site, Canvas student support site.